Now, what we've done is we've gone right the way through the QM course. There's just one tiny little thing that I want to do is to tie everything up, is to go back to modeling. And then on Monday, we have an additional lecture slot that's beyond what we need. So what I'm hoping to do on Monday is to know what questions you would like me to run through. So there are problems I've given you, and I'm prepared to run through any one of those questions or several of those questions on Monday. But I need you to guide me. I want to do problems that you're interested in me following. So have a look on Are You Connected? Have a look at the additional problems I've placed there. And by Monday, let me know what you want me to cover in Monday's lecture in terms of problem solving. But for today, I just want to remind you that we've come full circle. We started off with what molecular modeling is. We've had a look at molecular mechanics and how we can calculate ourselves energy of molecules. Then we saw the failures of classical mechanics and decided that we're going to replace everything with quantum mechanics. And we had the Schrodinger wave equation, and we ended the last session with that it is possible approximately to solve the Schrodinger wave equation for molecules, which means that we can use quantum mechanics to calculate energies for molecules. So we're now back to where we started with molecular modeling. And so the question is, how would we approach a molecular modeling problem with all that we have available? So here's an interesting problem over here. And it says it's been proposed that the thermal conversion of cis bicyclooctane into the octadienes involves the formation of the ZE isomer first. So the question is, how would one use molecular modeling to investigate this suggestion? So this goes back to where we started. In our very first lecture, we had a look at how we approach molecular modeling problems, and we say that there are 4 stages in trying to solve problems using molecular modeling. And the 4 stages are: 1, you have to define the problem. The second stage, you have to build the model. The third, you do some calculations. And then finally, you analyze the results. So I'm going to try and see whether we can't use molecular modeling to solve and to investigate the suggestion. So in the first stage, we've defined the problem. We know what the problem is. We want to know, is it possible that 2 gets formed before 3 when this ring opens? Is that possible? And so we'd like to explore it. So the way I would start in this problem is I would construct all 3 species. But there's a problem. Now I'm going to show you what that problem is that when you construct these, you're biasing, you bias the geometry in the way you construct them. So for example, let's have a look at system 3. I'm going to try and construct 3. So have a look at this octadiene. This is the cis octadiene, and let's see if I can construct it. So let me share a little program that I've got available called Marvin Sketch. Yeah, Marvin Sketch, we've got a site license for it, an academic license for it. So if you want it, it works under Linux, which is what I'm using at the moment. It also runs under Windows, and it's a really powerful program for dealing with systems. And I'll show you how powerful it is now. So I'm going to do that cis octadiene, and I'm going to try and draw it. So I need to make sure I've got 8 carbon atoms. That's 3, 4, 5, 6, 7, 8. So there we go. And of course, we've got to have 2 double bonds that are separated like so. Okay. So I have constructed this cis octadiene. Okay. But quite clearly, you can see that that perhaps the way I've drawn it is less than ideal. Firstly, the bonds don't appear to be the correct length. If we could measure them, it appears that there's a bond that's longer than the others. And secondly, we don't have any hydrogen atoms available. And so I'm not sure if these menus will be visible to you. Just shout if something hides. But what I'm going to do is I'm going to, on the structure, I'm going to just quickly add explicit hydrogens. So make sure that every atom is visible on that. And then I'm going to, on the structure, I'm going to clean in 3D. So now this is a much better version of the cis octadiene. But note that this appears to be an envelope conformation, which may or may not be the lowest energy conformation. I want you to think back to our second lecture or so, when we looked at the potential energy surface. If I were to optimize this, yes, it would go to a minimum, but would that be a local minimum or would it be the global minimum? So when you construct your molecule, that's a problem you've got to think about, because if you're not starting off with a global minimum, are you not biased in your analysis and your calculations in some way? So it's really important that you can do you do some kind of conformational search beforehand. So what I'm going to do is I'm going to share my whole screen for a moment. And that's a large amount. But the thing is that what I want to do over here is a calculation. I'm going to search for conformations. And let's search for conformations. And right, here we go. So I'm going to maximum is 10. And let's just search for conformations and see what happens. And I have some conformations that have come out from that calculation. So let's zoom in on those conformations. There's a question. Any questions? Okay. So have a look at these, and you can see here we go. This is the lowest energy conformation, and it's I rotated around. You can see that it is in a kind of a bent structure. I can't quite make out what it is from this, but I've got some higher energy conformations as well. And there is the envelope that we started with, and that's a higher energy conformation. So that's a minimum on the potential energy surface. But this here is the global minimum on the potential energy surface. So these are all minima. These are conformations. You minimize them, they won't change. They will be maintain that conformation. But of course, we've done a search and we've been thorough. And this undoes any bias that I put in the generation of that octadiene ring. So you must always search on the potential energy surface, not for local minima, but the global minimum, the lowest energy over all conformations of a system. And so we would then be able to select, and we'll be able to save, and we will be able to save, and the menu may disappear for you, but I'm just giving it a name in a folder as being, if I just need to give it a name, so bear with me for a moment and save it. And I need to save it as an appropriate file type. And so this is the I'm giving it a name. Okay, so now I've saved that as our lowest energy system. Okay, so we need to always define the problem, we construct the model. Now, yes, we have constructed the model, and of course we've saved it, and the chances are that we have saved it using Cartesian coordinates. If we were to have a look at the file I've just created, where I saved it, you open it up in a text editor, you'll find lists of X, Y, and Z coordinates. But bear in mind that the calculations we're going to do now are more efficient if the representation is in a Z matrix form. Okay. So what you want to do is you want to construct all three systems in this way, and you want to do a conformational search on all of them. You need to find the global minimum for all of those. So that's really important. That's where the starting point of what we're going to do. Okay. Then what we've got to do is, once we constructed all three of those, and we've got the global minimum for all three of those, the question is, we're going to do calculations, yes, define the problem, construct the models, do the calculations. But before we do the calculations, we've got to choose a model chemistry. So a model chemistry is something like what we discussed last lecture, Hartree-Fock, together with the basis set. So we could do Hartree-Fock with a 631 GD basis set, for instance. Would anyone here care to offer suggestion why Hartree-Fock might not be a good choice? Remember that in Hartree-Fock there were three approximations that we made. The Born-Oppenheimer approximation that everything has. So any quantum mechanics you do will generally have the Born-Oppenheimer approximation, so that's not going to affect your choice. And many also have the basis set approximation, so that's why we choose a basis set. But the Hartree-Fock approximation had this mean field, which means that electrons are treated as being in a field of other electrons. So electrons travel through a cloud, which means the cloud can't avoid that electron, which means that the energy will always be too high. So Hartree-Fock has this problem that the energy is always too high, and that is the correlation energy. So I wouldn't choose Hartree-Fock for this calculation. If I were doing this for a project and I had 20 minutes or so to do each optimization, or an hour or so, I would definitely be doing density functional theory, because DFT methods are a good balance. Check the last slide. DFT methods are a very good balance between speed and accuracy. So I would be using B3LYP as one of the density flavors of density functional theory, with a basis set like 631 GD. I would be using that. But of course, if I'm going to do it here in the lecture, I'll want something a bit faster. I'll use maybe a semi-empirical method. So like we've used in MOPAC, there's very fast and very approximate semi-empirical methods, just to illustrate what's going on. Okay, so let me go to a different program quickly. I just need to close things to make way and start up a new program. So just bear with me while I start up the next one. So I'm going to start in a different program, and the first so there we go. Right. So I'm afraid I have to share my screen again. So in dealing with this problem, I'm going to go straight to QM, and I'm going to have to use a different tool to, I'm using a different tool to draw compound number 1, which is one that we needed. So what I'm going to need to do is let's see if I can make the cyclic octadiene, or the precursor to it. So I need to have 1, 2, 3, 4, 5, 6, 7, 8 atoms. I'm going to quickly just remove some hydrogens and bond at a place to make it a cyclic system. And so I now have 8 atoms, which is fantastic. But now I need to make the first system, which was the bicyclic system. And I'm going to make the bicyclic system by connecting like that and bonding. But of course, in the bicyclic system, we had a double bond at this point over here. And so I'm going to just remove some hydrogens and make sure that this here is a double bond. Okay, and then when I clean this up, as we should always clean up, you see that this here is perhaps not the best conformation, but of the bicyclic system. I'm just going to do my own kind of conformational searching by adding hydrogens and removing them, because I want the cis bicyclic system, so that when I clean it, that hopefully we will end up with a decent geometry. So now that we've chosen a model chemistry to go forward, we can do some calculations using that model chemistry. So I'm going to set up some calculations, and the first one that we want to do is a geometry optimization. So we've constructed the molecule, and maybe what I need to do is an optimization with a frequency analysis at the end. And the method, Hartree-Fock, we said is no good. We would prefer to use density functional theory, which might be B3LYP, but of course in the lecture I'm going to just use a semi-empirical method like PM6 or AM1. And I'm actually going to use AM1 for this. Very fast quantum mechanics. It's very fast, and it will get us a result quickly. So let's save this as this is molecule 1 and submit it. And then when you're getting a computer to do the QM for you, you have to be extremely patient. I showed you in the lecture yesterday that QM is quite intense in terms of all the interactions, and you have to have all these approximations. So it does take a computer a while to work. And you see, I've now had success. So let's open the log file and see what it looks like. And there we go. Here we go. Here is the optimized system, which is fantastic. It looks like I have some kind of envelope conformation. I seem to have a reasonable conformation on the cyclohexane side. And this is the system I want. Now, in order for 1 to go to 2, there's a ring opening. And if I go back to our problem, there's a ring opening. So 1 to 2 or 1 to 3, there's a ring opening. So what I want to do is I want to try and break the central bond and see what happens. So I can break that central bond doing what we've done in the past, is we do a scan. And so I'm going to, in this program, we work slightly different. And we have redundant coordinates. And so what I'm going to do is take that bond, which is a bond, and I'm going to break it. I'm going to make it, I'm going to scan that bond. I'm going to take 10 steps of 0.1 angstrom, so get longer and longer 0.1 angstroms apart every time and see if I can break that bond. Hopefully, by breaking that bond, I'll end up, we'll have the bonds moving around the cycle. So we'll have this pair of electrons forming a double bond here, this one forming a double bond here, and that will be our octadiene that we're trying, our cyclooctadiene that we're trying to create. So let's try and do that calculation. So let me just check that I've got the redundant coordinates set. Scan 10 steps of size, that's perfect. And so when I do calculate, Gaussian calculation setup, and here we go. In this case, the job type is I want a relaxed, and I'm going to scan it. And so let's see what happens. So now I'm trying to scan. Let's see what happens. Just hang on. I just want to remove some of the questions that it has. It's fine. Okay. Okay. So now we're trying to just scan that bond. Just apologies, I'm just seeing and apologies, there are some problems on that, so I'm just removing all references to previous runs. So now we've got the scan going. So what it's going to do is going to start off by calculating the energy of the system. It's going to move those atoms 0.1 angstroms apart, give us an energy, 0.2 angstroms apart, 0.3, all to a further additional 1 angstrom. So we have now completed, and so now we have the scan. This is exactly like what you've done in WebMo. I'm not using WebMo because our system in WebMo only allows for a maximum of a certain time in calculation, and I'm just worried that I might overrun the time if I work that. So here we go. I've done the scan, and if I have a look at the results of the scan, you can see it's really interesting that as you move the atoms apart, the energy goes up. You can see the energy goes up to a point, reaches a maximum, and then it starts decreasing on the other side. And you can see that on the decreasing on the other side, it's forming over here. It is forming the octadiene. So the most important part of this scan, the most important part over here is this point up here, because this here is going to be our transition state. We need to explore that transition state. And because we have discrete steps, our transition state might not be exactly at that distance. So what we can do is we can do a transition state optimization on this point. So if we take this point here and we go to calculate, we can do a calculation setup. And what I'm going to do is job type. I'm going to do an optimization, and I want to optimize to a transition state, and I need to calculate force constants in these ones. We have to do that, and just need to just take away our scan from that, and let's see if we can find a transition state. We can optimize to a transition state on this system. So this is now a transition state search for this. Right, and so be patient. You have to be patient with quantum mechanics. Particularly if you're doing a transition state search, you're going to have to do a single point. Okay, and there's an error on that, so let's have a view and see what the error is. Okay, my apologies. It could be something to do with my geometry. I think I know what the problem was. Yes, and so I'm going to do that calculation again. The problem was the curvature of the potential energy surface as it's trying to find. You can imagine that if you're trying to find a minimum, it's quite easy. You just go down and down and down. But if you're trying to find a transition state, the transition state, you can't just go up and up and up. You have to be very careful about trying to find the valley between the mountains. And so it has to know a lot about the about that. And so we have to just be very careful when we try and find, you need to know the curvature of the potential energy surface. And so that's partly why I wanted to, so I can maybe ask it not to just find the curvature of the potential energy surface once, but maybe several times. This is another reason I didn't really want to use WebMo for this, and I prefer to use Gaussian. So if you're doing computational chemistry, it's a bit like doing work in the lab is, there we go. It has completed, so the transition state. So it's a bit like doing work in the lab, is that you don't always have a successful reaction. You don't always have a successful run, and so you always have to adjust your experiments and find out what's gone wrong, troubleshoot to eventually get a successful conclusion. Now this here has been optimized to exactly the transition state. Now, there was an important type of calculation that I mentioned in the first lecture that we did, and that important type of calculation was a vibrational analysis. And I said a vibrational analysis is important on many fronts. Firstly, a vibrational analysis will give you the theoretical infrared spectrum. The second point is that if you do vibrational analysis, you've got the vibrational contributions to your free energy. And of course, when we had a look at vibrational spectra, we remember that there is a 0-point energy. No molecule can ever have zero vibrational energy. And that's as a consequence a little bit of the Heisenberg uncertainty principle. You can't have a molecule stationary because then you know everything about its momentum and position at the same time. But there was another reason why you do a vibrational analysis, is to characterize the potential energy surface. And of course, if you do a vibrational analysis and you get imaginary frequencies, then you know you're at a transition state. If you only get real frequencies, then you know you're at a minimum. So I specifically, when I did this calculation, I asked the software to do a vibrational analysis right at the end. And so let's have a look at the results of that vibrational analysis at the end, and let's see what we can see. And you can see that the first is written as negative 642 centimeters minus 1. That negative really means it's not a negative, it's an imaginary number. So the frequency is imaginary. And you can see that I know that I'm at a transition state because I've got exactly one imaginary frequency. And if you were to animate it, let's just do a very slow animation of that. So can you see that? That animation of that imaginary frequency shows you the forward reaction and the reverse reaction that we found for this transition state. Okay, so let's stop that animation. So what I've done is we constructed molecule number 1. We did a scan. We found the highest energy. I've refined it. I refined it, optimized it to exactly the top of the hill, to exactly the top of the hill. And doing a frequency analysis shows me that, yes, I definitely have a transition state over here. Can I go back to our original molecule? Our original molecule, if I can find it over here, just hang on. Our original molecule I also did, just hang on, just want to find my other one, and I might have to open it again. The original optimization that I did, so there we go, molecule1.log. So our original optimization, I also, this was our starting point, and I optimized it. So this is hopefully a minimum on the potential energy surface. I also did a vibrational analysis on that. And so when you now have a look at that, you'll see that for this molecule, we have only real frequencies. So I definitely know this is at a minimum. And because I know the vibrations of it, I've got the normal modes, I've got the vibrations for both of these, I will have, in the log file, I'll have an accurate free energy for this system, and I'll have an accurate free energy for this system. And if you've got an accurate free energy for your starting point and an accurate free energy for your transition state, then you can be absolutely certain. You can be absolutely certain that you know the free energy of activation for this reaction. Okay. So at the moment, I have got a starting material. I've got a transition state, and we might, it might be nice to explore, if I go back to the scan, it might be able to explore what the product is of that. So I'm going to simply open the product that we had. Let's close the vibrations since we know what they are. Okay. And maybe I can start with our final point over here. And so that was our final system over here. And let's see if I can calculate over here. And let's optimize it. So let's see if we can optimize our final system. As I just want an optimization and a frequency analysis. I don't want to write that. And let's submit. And this certainly looks very much like the cis trans. So it looks like molecule 3 to me. Okay, and again, I'm using QM to do this optimization. So it does take time, but of course, if I was using V3LIP or other density functional methods, we would have to be very careful about that. It would take some time. And so here we have, here is the other side of it. This is the product that's formed when you pull that bond apart. And so let's just have a look at the results and check the vibrations, check that this is a minimum. And yes, it is a minimum. I've only got real frequencies there. So I would be able to have a look at the infrared spectrum, for instance. Here's the predicted infrared spectrum, and I have a product. And at the moment, this looks like it is too. So my exploration of this problem that we have seems to suggest that we are going to get, can you see there's a trans geometry here and a cis geometry here. So it certainly appears that the transition state that we have found is leading, of course, to the particular system that we see here. So if I can just summarize where we've gone and what we've done. So if I can find Here we go. So our problem was, it's been proposed that the thermal conversion of 1 into 3 involves the formation of 2 first. So what we've done is we construct all of these first. We make sure we find the global minimum of these first. We've defined the problem. We've constructed the molecule. And we've chosen a model chemistry to do calculation. And I would never choose semi-empirical methods. I would always choose something a little more involved than that, like density functional theory with a good basis set, like a double zeta basis set, like 631G with polarization functions. So I'd always choose a good density functional theory method with a good basis set to do these calculations. Right, and so then what we've done after that is we've optimized them with a frequency analysis. We should have also optimized all the other things with a frequency analysis. And the frequency analysis means that we would have good free energy values for all of those, as well as confirming we're at the bottom at a minimum, as well as the infrared spectra. Then what we did after that is we did a scan. We pushed that bond apart. We found that the energy reached a maximum before dropping off. And so that maximum we decided was a transition state. So we optimized that maximum to a transition state, and we confirmed that the vibrational analysis that there was an imaginary frequency. And so we knew we had a transition state. And then we had a look at the other side of the scan, we optimized, we found that it was 2. So what we've got is we have an energy value for the starting point, we've got an energy for the transition state, and we've got the energy for a product. So certainly, the evidence that we have collected so far really does seem to suggest that 1 forms 2 first before going on to 3. Okay, so if I can just summarize, when we do it, we define the problem. We've got a big problem. Second thing that we do is we construct the model. And of course, we can have it in Cartesian or Z matrix coordinates, but we must find the global minimum. Third thing, we've got to do the calculation, but before you do the calculation, you've got to choose a model chemistry. And we've got a lot of choices. We could do Hartree-Fock, we could do MP2, we could do semi-empirical. We do molecular mechanics would not work here because you've got to break bonds, but a good choice is always to use density functional theory as a good balance between speed and accuracy. Then you do the calculations, and the calculations in this case involved optimizations and scans. Many of the optimizations were to minimum, but one of our optimizations was to a transition state. And then finally, our final point was to do the analysis. We have the energies of the systems, we have the energies of transition state, and so we can get the activation energy of the system for the reaction. And of course, if I asked you to discuss this problem, you wouldn't have the results. So you would only surmise that maybe after the scan, after the transition state, we would be able to find what it led to. Are there any questions about the procedure for molecular modeling? Is this kind of procedure, would that be something that would be interesting? Some of you already know your internship projects, and I'm not sure what's happening with the internship projects, but you might have reactions that you're interested in doing in those projects. Would this kind of calculation be useful to any of you? Those may be doing organic chemistry or organic synthesis. So just think of this as an idea of how you can explore and how you can study things from a theoretical perspective. Okay. So if there are no other questions, then what I need is I need some feedback from you then as to, I know I don't have a chat on, I'll just see. can see no questions in the chat. So please, for Monday is our last QM lecture. And Monday, I would like to be working through the most difficult problems, the ones you're struggling with. And then, so from the QM course. So please take it Monday, that's what we'll do. Tuesday, I'm still lecturing you on Tuesday, but Tuesday is unlike anything that we've done so far. Tuesday is more organic chemistry. It's not quite organic chemistry, but it's closer to being organic chemistry than it's much closer to organic chemistry than it is to physical chemistry. So it's a total change of gear, and we'll have to we'll be getting out of a mindset of QM and back into the mindset of mechanisms in organic chemistry on Tuesday. But please let me know by Monday what problems you'd like me to address during Monday's lecture. Any questions, any comments? Okay, if there are no questions or comments, I'm going to sign off for that, and I'll see you at 11 o'clock on Monday.